AC through a capacitor. Let us consider a capacitor of capacitance C. This C is connected with alternating EMF so that current I flows throughout the circuit. We know that instantaneous EMF E is equal to E naught sine omega t. Let it be equation number 1. Let I be the current and Q be the charge over the capacitor. Then instantaneous potential difference across the capacitor is equal to Q upon C, where Q is charge over the capacitor and C is capacitance of the capacitor. Now the instantaneous EMF is equal to instantaneous potential drop across the capacitor. Therefore, E is equal to Q upon C, or we can write Q is equal to EC. Now, substituting the value of E from equation number 1, we get Q is equal to C E naught sine omega t. Differentiating both sides with respect to time, we get dq over dt is equal to d dt of C E naught sine omega t, or C ddt of q, differentiation of charge with respect to time, is current I. So we can write I is equal to C E naught cos omega t into omega, or we can write I is equal to E naught divided by 1 upon omega c cos omega t. From trigonometrical identities, we can write I is equal to E naught divided by 1 upon omega c sine omega t plus pi by 2. Here 1 upon omega c has got the unit of resistance. Let 1 upon omega c be xi c. It is called reactance of capacitor or capacitive reactance. Capacitive reactance or reactance of capacitor. Now, if E upon xi c is equal to I naught, then we can write I is equal to I naught sine omega t plus pi by 2. Let it equation number 2. From first equation and from second equation, it follows that AC leads. AC leads, alternating current leads EMF by phase angle pi by 2 when alternating current AC passes through a circuit containing a capacitor. Students, we have two equations. First, E is equal to E naught sine omega t, and second one is I naught sine omega t plus pi by 2. So you see the graphical representation. Now here we are plotting a graph between EMF or current in this axis and omega t on this axis. So, see, on y-axis we have considered EMF, E or current, alternating current, and on x-axis we have considered omega t. So, we have a graph, sinusoidal graph. Solid line represents EMF, whereas dotted line will represent current. Phasor diagram. Phasor diagram, you see this straight line will represent EMF, and EMF is making an angle of omega t with the axis OX, or this EMF makes an angle of omega t with x axis, whereas the current, see, current makes an angle of pi by 2 with EMF. See, in this particular circuit, when we have considered capacitance, capacitance is connected with EMF, alternating EMF, and for this particular circuit, as current leads the EMF by an angle of pi by 2, so this current makes an angle of pi by 2 in anti-clockwise direction with the phasor representing EMF E. So, see, it may be noted that first point, the peak value of alternating current I naught is equal to E upon xi C, which is capacitive reactance, and second point is the capacitive reactance xi C is equal to 1 upon omega C, since omega is 2 pi f, 2 pi into frequency. So substituting, we can write this capacitive reactance is equal to 1 upon 2 pi f C. This quantity is complete quantity, or you can say capacitive reactance is infinite for DC, direct current. Why? Because for direct current for DC, frequency is equal to 0. And if you substitute 0 here, you will get infinite capacitive reactance. And the value of frequency for AC is not 0. Therefore, we can get small value of AC. For this capacitive reactance, we get small value for alternating current. It means a capacitor serves as a block for DC, and offers an easy path to AC. See, when we plot a graph between capacitive reactance on y-axis, and if we consider frequency on x-axis, then we get this type of curve for capacitive reactance versus frequency graph.